Right. So welcome to the second part of our 2011 and 2111 seminar. I'm Ronald and I'll be going through Fourier series and vector fields, and the next part is going to be taken over by Tim. So let's get started. Of course, we'll be first getting started off with Fourier series. Alright, so let's just define what an inner product is. So an inner product is a binary operation. That just means it takes in two things and then produces another thing. The most basic example of a binary operation would be, for example, addition. It takes in two numbers, uses a symbol that symbolizes we're using this binary operation, and then it gets performed to produce a single thing. So, for an inner product specifically, it takes in two vectors and then it outputs a number. So, generally we denote an inner product with these angle brackets, and then we write the first vector we're putting in, then the second vector, and then the ending angle bracket. And an inner product is pretty simple. It's just any operation that satisfies these following conditions. The first one is that it's non-negative when you do the inner product of a vector with itself. And if you do this inner product with itself and it's equal to 0, then the vector must also be equal to 0. It's also linear and it's also commutative. So that means if you have a plus, you should be able to split up the inner product, and if you have any scalars, you should be able to take it out of the inner product and multiply the inner product by that scalar. And of course, commutative means that it doesn't matter what order you put the two inputs in. So it could be VU or UV, both of them produce the same inner product. Now, I think we can get started with an example of an inner product. The one you might be familiar with is the one with two vectors, and it's the dot product. So we can just quickly see that it does follow all of these rules. For example, if we dot 1, 1, 2 with itself, so in this case 1, 1, 2, we use a dot for the dot product, and of course that would be 1 times 1 plus 1 times 1 plus 2 times 2, which is going to be 1 plus 1 plus 4, which is 6. And of course that's greater than or equal to 0, and we're dotting it by itself. And of course if we took itself and it was a 0 vector, then it would produce 0. So that's our second condition. And of course, you might have seen we should be able to use the notation from before, where we have an angle bracket, we write our first vector, our second vector, and then another angle bracket. And this is another way we can represent using the inner product. So we also know that if two vectors have a dot product which is equal to 0, then we call them orthogonal. Now, we can also use this kind of logic in the inner product for functions. So generally we'll be working with continuous functions defined from A to B, where A to B is a domain. And so CAB represents the space for every single continuous function between the interval A and B. So if we have two functions, f and g, the inner product of these two functions is the integral from a to b of f times g. And just to give some intuition to why this might be similar to the dot product that we know, when we use our dot product, we look at each component, multiply them together, and add them all overall. So what we do is we look at the first component, right? We have a 1 here and a 1 here. We multiply them together, and then we add that to, looking at the second component, a 1 and a 1, multiply that together, and then add it to what we already have to get a 2. Then we have a 2 and a 2 in the third component. We multiply them together, and then add it to what we have, which is 6. So, similarly, what we are doing is we're taking two functions, and for each point, we're multiplying them together, right? So that's what it means to multiply these two functions. At every individual point, we're having the values multiplied together. And then what we're doing is we're summing it up through area, which is why we use an integral. So what we're doing is we're just multiplying the two inputs at every single point and then summing it together. And of course, we have an f and a g, which are our functions, and if they have an inner product which is equal to 0, then we call them orthogonal. So, how exactly can we show that this is a valid inner product? The way we do it is, first, of course, we have our inner product, which we've defined. So the inner product between f and g is the integral of f times g from a to b. So, seem to have dropped something. The way we can show that it is we are going to show that it satisfies the 4 conditions. So we can just check through each one. The first one is that if you have a inner product with itself, then it's greater than or equal to 0. The way we can do that is we know that the inner product with itself is actually just f times f integral from a to b. F times f is of course f squared, and since f squared is non-negative, the area under f squared's curve is also non-negative, so we can say that the integral from a to b of f squared is non-negative, which proves our first statement. Now we can go to our second statement, which means if you dot f and f together, then it must mean that f is equal to 0, or if you have f equals 0 and you dot it by itself, you also get 0. So the way we can prove this is we have the dot product being, the inner product being equal to 0, and we know that the inner product of f and f is going to be the integral of f squared from a to b, which is what we have, and we know that this means that f is equal to 0. And the reason f is equal to 0 is because if it wasn't, maybe we had a function and then there was like a spike. Of course, this has an area, and so if we take the integral, it's not going to be equal to 0. And we also can't have functions where it's an open circle here and then maybe there's a value up here, because we know that it must be continuous. So there must be a way from down here to connect up here and back down, which guarantees that we have a non-negative area. And also the integral can't be negative, because any function with a negative value, when you square it, will of course become positive. And so the area of this f squared is still not equal to 0. So that basically just shows that if we have an integral from a to b of a function and it's equal to 0, then this function must be 0. And of course that proves our second condition. So now we can prove our third condition, which is linearity. And the way we prove linearity is just using the definition of the inner product. We can write it out, and what we see is that we can multiply this first term by h and this second term by h, and that's how we get these two integrals. And since these are constants, we can actually take them out of the integral right here, and we see that these two integrals by themselves are also inner products. So this is the inner product between f and h, and this is the inner product between g and h. And so we get our final statement, which proves linearity. Now, we can move on to our final condition, which is commutative properties. So, what we can do is we can easily see that the integral of f times g is equal to the integral of g times f, because multiplication is commutative as well. So what we've shown is that the inner product for f and g is the same as the inner product of g and f. So now that we've verified all four conditions, we've shown that the inner product for the space of continuous functions from a to b is valid. Now, let's go ahead and look at what a norm is. A norm is just a way to quantify length, and it can be anything as long as it follows these four rules. So the first one is that it's always non-negative. Obviously, you want length to never be negative. And if the norm is equal to 0, then what you're putting in is also equal to 0. And the norm of something times a scalar is equal to that scalar times the norm of the original vector. And then, of course, the triangle inequality. So it just says if we have two vectors and then we add them together to get a third vector. So this larger one vector is always going to be lesser in length compared to these two smaller vectors that add up to it, but have its lengths added up individually. So this length plus this length is always less than this longer length. So, of course, a norm is a map from a vector space to the reals, which means that it takes in a vector, and we can denote the norm with these two lines on the outside. So it's like a modulus, except you have two of them, and then you put in the vector that you want, and we call this the norm of U. So there are also some other properties. The first one is that if we have an inner product, the square root of a vector by itself is always equal to some form of a norm. And of course, we can verify this a bit with dot products later. So we also have the Cauchy-Schwarz, which means that the inner product is always less than or equal to the norm of the two vectors in its inner product. Now, we have the norm of a vector space R to the n, where this means that the vector is an n-dimensional vector, right? So the norm of some vector x, and of course, in this case, x is equal to x1, x2, and so on until xn, is x1 squared plus x2 squared plus x3 squared, so on until xn squared, and then square root of that. And what you might notice is, if we dot this vector with itself, we would get x dot x, which is equal to x1 squared plus x2 squared, and so on until xn squared. And if we take the square root, we find that this is our norm. So this kind of just shows that this condition is true, where the norm of U can be given by the square root of the inner product with the vector with itself. So we can extend this to our space of continuous functions from A to B. So the norm of a continuous function, f, can be given by the square root of the inner product with itself. So since the integral from A to B, f squared x dx is equal to the inner product of f with itself, if we take the square root, then we can define it to be a norm of f. And there's a 2 down here because it's called a L squared norm or a mean square norm. And even though this is a possible norm, it doesn't mean that it's the only norm. So there are an infinite amount of norms. This is one of them. And another one that you might see in this course is the max norm. And what that does is, if you have a function it takes the maximum absolute value. So in this function, if this was the x-axis, it would take this point right here, and that value would be our max norm for this function. So, of course, an example is maybe x squared from 0 to 1. And so that would be something like this, where this would be 1, and this would be 1. Of course, our max norm, which is our maximum absolute value, is going to be equal to 1 in this case. But if we looked at minus x squared, which looks like this, and of course this is going to be minus 1, we are looking at the maximum absolute value. So since minus 1 is our largest value with largest absolute value, our norm for x minus x squared infinity, so this infinity sign just means that it's the max norm, it's going to be equal to 1. So now we can get into Fourier series, and it might look a bit complicated here, but Fourier series, literally just remember this one formula and you're good to go. So it's a way that we can take a periodic function and then put it in the form of a sum of coses and sines. And of course, we also have coefficients, an and bn in front of these coses and sines. And then we have an a0 term divided by 2 on the outside. Now, on the inside of our cos and sines, we also have an n pi x on L. So you don't really need to worry too much about what this means, but it's just good to memorize n pi x on L. And so we have a couple facts. For Fourier series, generally what you're going to be asked to do is just to find the coefficients a0, an, and bn, right? And then determine where does it converge. That's generally what a Fourier series question is going to be like. We'll go through it, but all you need to know is that it's 2L periodic. So for example, if we know that the period is 6 is equal to 2 times 3. So in this case, L is equal to 3. And more commonly, if it's 2 pi periodic, we know that 2 times pi is equal to 2 pi. So L is equal to pi. So generally, we'll look at what function we're trying to approximate and then let our L value be half of the period. So first, I want to look into why we might use Fourier series. So the good thing about Fourier series is that it can be used for almost any possible periodic function, and then turn it into sines and cosines. Well, I guess the first thing you might ask is, why might you use Taylor series? Well, what Taylor series does is it takes a really ugly function, puts it into a polynomial, so it's really easy to differentiate, integrate, and find values. And in the same way, in a similar way, Fourier series tries to approximate functions which might be difficult to express in terms of continuous functions. So the power of Fourier series can be demonstrated with the use that they can actually describe non-continuous periodic functions, which we'll get into with an example. So one of the most common types of functions that are approximated is a kind of square-looking function, and we can see it right here. So generally, we have a bunch of cos terms and sine terms, and then as we add more and more, it starts to approximate this curve that we're trying to find. And so generally, with one sine term, obviously it won't look too similar to what we're trying to get, but as we keep adding more and more sine terms, so we see as each slide progresses, we're adding another sine term. It seems to kind of approach this square-like block pattern, and that is the function that it's trying to replicate. So what you might notice is that, of course, it's not exact, which is why it's an approximation, but it's pretty close, right? Like, this is a very hard function to replicate. The main reason is because it jumps from this point to this point, so of course it's discontinuous, and it's really hard to describe discontinuous functions. But the thing, so like generally you would have to use something like keeping track of regular intervals, and then at each individual point you find the value it's at. So you are storing a bunch of points to replicate this curve, right? But instead, if we notice in Fourier series, we only need a couple numbers memorized. And with these 4 numbers, you're able to replicate this entire curve. And so, one way that you might use Fourier series is in compression. Like, obviously, sound waves, they're just a bunch of waves, so you should be able to characterize them in Fourier series. And instead of having to memorize the whole sound file, you can just memorize a couple numbers to represent this Fourier series. And yeah, you've replicated the sound wave and you've saved a bunch of space. So now that you know why we might want to know Fourier series, why is it, like, how exactly do we find the coefficients? Well, we can look back at linear algebra and just think of how we might, given a basis, decompose a vector v. So when we're given our orthonormal basis, so for example in 3 dimensions, we have E1, E2, E3, and this is equal to 100, 010, and 001. How exactly do we get 1, 2, 3 to become 1 times EI plus 2 times, 1 times E1 plus 2 times E2 plus 3 times E3? So the way we do it is we take this vector and then we dot it with our vector right here, and we would get 100 dot 1, 2, 3, and of course that would just be 1 times 1 plus 0 plus 0, so that gets us 1. And that's pretty much it. So we can keep doing that with our bases, and that's how I get our coefficients. But let's say that we weren't working with these orthonormal bases, and instead we were working with a more general orthogonal basis. So what we were actually doing is, maybe given an axis and a vector, we were seeing how much does this vector go in this direction. So if it goes in this amount in our x direction, we might label that as the coefficient to our first bases. And then we look, how much is this vector going in the vertical direction? So this might be how we find our coefficient for our vertical basis vector. Well, in the same way, if we have maybe this as our basis, which is perpendicular, and maybe a vector right here that we're trying to find in terms of these bases, what we see is that what we did was find the projection of this vector onto our basis vectors. So in the same way, we can find the coefficient of our vector by first just projecting this vector onto our basis vectors. Because projection just means how much is our vector going in this other direction. So this lets us just decompose our vector v with a projection times the basis vector, and then summing up all of these coefficients times basis vectors. So, of course, we can also see that this is a dot product, and so we can just simplify it to a inner product, and then we have a norm squared down here. Now, how do we apply this to continuous functions from minus L to L? Well, first, what we notice is that we have an orthogonal set here. So what we can do is, since all of these are orthogonal, you can check this by yourself, by the way. You can take any two vectors, maybe 1 and cos. No, first maybe I'll explain what this set means. It means we have a 1, and then we have every possible cos n pi x over L. So it includes cos 1, so x pi x on L, but it also includes cos 2 pi x on L, cos 3 pi x on L, and so on. But then it also includes sine pi x on L, sine 2 pi x on L, and sine 3 pi x on L, and so on. So what we can do is we can take any two functions here, let's say 1 and cos x on L, take the integral from minus L to L, and that'd be equal to 0. But of course, you can also put in a sine 2 pi x on L here, or you can take the integral from minus L to L of sine 3x pi on L multiplied by sine pi x on L dx, and that's also equal to 0. So any two functions you find the inner product of, it's going to be equal to 0, and that makes it an orthogonal set, which means every function in here is orthogonal to every other function in here. Now, since this is true, we can use it as a basis, and so how can we derive the coefficients an and bn? Well, we know an is going to be the coefficient of cos n pi x on L. So the way we do it is we have this as our basis vector, and so we want to project f onto our basis vector. And the way we do that is we need to use the inner product between f and our cos, and we see that here, where it's the integral of f times cos from minus L to L, and then we need to divide it by the norm of cos n pi x on L squared. And we'll discuss later that the norm of cos n pi x on L is actually equal to root L. So 1 on the norm of this cos is going to be equal to 1 on root L squared, which is 1 on L. And that's what we see right here. And in the same way, bn is the coefficient of sine n pi x on L. So we find the inner product with sine and f, and then we multiply it by 1 on the norm squared. And that's how we find our coefficients. And of course, we know that since we did it more generally, n can be applied for 0, 1, 2, and so on for our an terms, and then b can be applied for 1, 2, 3, and so on for our bn terms. But you should also be warned, sometimes this integral could have like a 1 on n times cos whatever, and it just makes it hard because you can't exactly sub in a 0 into 1 on n, so sometimes we have to find the integral of a0 for ourselves. And of course, we can now show that the norm of cos n pi x on L is equal to L squared. And the way we can do that is with our L squared norm. So if you remember what our L squared norm is, it's going to be the square root of the inner product of our function with itself. So that's why it's a cos squared and pi x on L from minus L to L. So since this is an even function, we can multiply it by 2 and then cut the bounds from minus L to L to 0 to L. And what we can do is we can multiply these two out, so these cancel, and then we can do the integral from 0 to L of 1, and that gets us our L here. Now we can compute this integral right here, and we should be able to get 1 minus 1, which is of course 0, so we're left with root L, and that's our norm. So, looking back, we see that this 1 on L is actually just 1 on root L squared, because root L is our norm. Now, we have the coefficients of our Fourier series, which is pretty much like 80% of the battle. So we have our Fourier series right here, and what we can do is we also need to know that A0 usually has to be calculated on its own, which is why we have n equals 0 right here. And if n equals 0, obviously this n becomes a 0, so it becomes a cos 0, and that's equal to 1. So since this term is equal to 1, it just becomes an f of x, which we're integrating from minus L to L, and then we multiply it by 1 on L. So these are the three formulas that you have to remember, and once you remember them, you're pretty golden, because usually they'll just ask you to find these three coefficients, and usually they won't ask you to put it into this form, or they'll give you this form, so you don't have to memorize the Fourier series form as long as you have the coefficients. So yeah, just remember these three formulas. And the other thing about Fourier series is we have the fact that when we're approximating odd functions, an is equal to 0, and that's because all of sine are odd. So if you're adding an even function to what we're approximating to be an odd function, then of course this cos is going to ruin the oddness, which is why we only have sines, and so an is equal to 0. But in the same way, if f is even, then since cos is even, we would only have cos terms. Since if you add two cos functions, it's going to be an even function overall. But if you add another odd function, like a sine, then it's no longer going to be even. So generally, if you find that f is even, then we can just say bn is equal to 0. So this is a really useful trick. Just try to find odd and even. Generally, it's a really big time saver because you won't be having to calculate one of these integrals. So let's look at a function right here. So this is a question from 2022, and it's a 2 pi periodic function. And we also have our function right here. So it's defined as 1 minus x squared from minus pi to 0, and then 1 plus x squared from 0 to pi. So generally, we're going to be asked to sketch it. That's our first part. We're going to be asked to find the coefficients of our Fourier series. That's our next part. And generally, there's a third part on convergence, which we'll discuss later since we haven't talked about what it means to converge yet. So, how exactly do we sketch this? Well, it's pretty simple. I generally look at these 3 points, right? So these are the discontinuities, or maybe when the piecewise function swaps from each branch to another. And just draw out the axes first. Label your points. Maybe you want pi to be here, 2 pi here, and 3 pi here. Pi to be here, 2 pi here, 3 pi here. So we have pi, 2 pi, 3 pi, minus pi, minus 2 pi, minus 3 pi. Now we can just look at our critical points. The first one I might look at is 0 because it's pretty easy. For each branch, if you put in 0, you get 1. So this is 1. And then we also have, when you have pi, so if you put pi in here, we get 1 plus x squared. So 1 plus pi squared, that's maybe about, I don't know, maybe like 10 something. We'll just put it up here. And since it's kind of like a parabola shape, we can just draw out a parabola kind of shape. And this is our 1 plus pi squared. And then we also have a 1 minus pi squared for our other point, which is going to be minus pi. So since minus pi squared is pi squared, it's just going to be maybe around here. It's going to be a 1 minus pi squared. And remember that this is actually an open circle because it's not equal at this point. And then we just want maybe a parabola kind of motion and to connect up. So this is our branch that we're given from minus pi to pi, but we know that it's 2 pi periodic. So what that means is we can just repeat it again on each side. So it starts off with an open circle, and then there's a 1 here, and then there's a closed circle, 1 plus pi squared. We get a parabola kind of shape on both sides, and that's this branch done. And now we can copy it here. It's a 1 here, 1 plus pi here, and then a 1 minus pi squared here, and it's an open circle, remember that? Whoops, maybe that's too low. So of course now we can connect it up in a parabola-like shape. But remember that it includes the endpoints as well. It's equal. So we just need to make sure that every single point is covered. Since minus 3 pi is not covered, we can look at the point, 2 pi above it. So minus 3 pi plus 2 pi is minus pi. And we see that it's going to be 1 plus pi squared. So we can just copy it and get our point. And this is pretty much our graph, where we just show that these are all equivalent points. Sorry, give me a sec. So, now that we've graphed it, I think we can start looking at our Fourier series. So what you might have noticed is that I did mention that it's 2 pi periodic, which is 2 times pi. So what that means is we can get our L to be equal to pi. So what you might notice is that they did give you the form of Fourier series, and it's a k pi in here. Usually it's an nx pi on L, but if L is equal to pi, these two cancel out, so you just get left with an nx, and that's what we have. So, although we notice that in here, it's not an odd or an even function, what I noticed was that it was actually an odd function that was shifted up. So if we define an odd function, g, which is minus x squared from minus pi to 0, and then x squared from 0 to pi, what we actually get is f of x, which is equal to 1 plus g of x, right? Because if you add 1 to each branch, you get what f of x is. So with this fact, we can start handling the integrals. So first, I'd like to find what a0 is. And so a0 is going to be f of x integral from minus L to L, and then multiplied by 1 and L. And since we know that L is equal to pi, we can just write it out like this. And then, of course, we use the fact that our f is equal to our 1 plus g. And then we can just split the integral, right? So this is the integral of an odd function from minus pi to pi. Since the bounds are in the form minus a to a, we can say that this integral is 0 since g is odd, and then we can just evaluate the integral of 1 from minus pi to pi, and since that's equal to 2 pi, we have 2 pi times 1 on pi is equal to 2. So our a0 value is 2. Now we can look for our general AK, and in the same way we know that our formula for AK is going to be equal to 1 on L times the integral from minus L to L of f times cos. And so what we can do is we can sub in the fact that we know what L is. L is equal to pi. We sub in all of the L's and then we get this integral. Now we can sub in the fact that f is equal to 1 plus g, and then split the integral. We know that this is odd, but this is even. And even times an odd gives an odd function, so this whole integral is equal to 0. Now, we also know that this is a cos function, so since it's just a cos function, we can integrate it normally. So it's 0 here because g times cos is odd, and so we can just evaluate our integral and then we get 0. Now what we can do is we can find our bk value, and in the same way it's an integral of 1 on L times f of x times sine from minus L to L. And of course we know what pi L is equal to pi, we sub everything in, and we of course also have f equal to 1 plus g. We split the integral, and we know the fact that g is odd and sine is odd, so overall it's even. Now this is also sine, so we can do the integral by itself. So if we calculate the integral of the sine, we get it's equal to 0, but then we can shrink the bounds from minus pi to pi into 0 to pi, and then multiply by 2 since it's even. And now we can just use the fact that g is equal to x squared in this range. So if we look at our g of x, we get g of x is equal to minus x squared, but it's minus x squared when it's between minus pi, and 0, and then it's x squared between 0 and pi. Since the integral's from 0 to pi, then we only consider this branch because this branch is now irrelevant. So we can just sub in x squared. And with x squared, you'll see that we can just perform by parts. So we're going to be integrating our sine because it hops between sine and cos and doesn't exactly gain an x value. But every time we diff this term, it's going to go down by 1 power. So if we integrate it by parts twice, then we should be able to evaluate it, which is what we do right here. And so if we find the first by parts, then we can get our first part of our term. Then we can by parts our second integral. And if we evaluate everything, we should get this bk right here. And the thing is, the question actually asks us only to find the coefficients a0, ak, and bk. So for now, we don't have to do anything with our coefficients. We found them, and so that's the end of our question. So now we're going to go into notions of piecewise continuity. And what piecewise continuity says is on a piecewise continuous function, every point has to have a left-hand limit and a right-hand limit, and it must be discontinuous at a finite amount of points. So, what does this mean? It means that, first we know that any continuous function is piecewise continuous, because obviously if we just have a normal function between maybe a here and b here, then of course it's not discontinuous anywhere, so that's 0 is a finite number, and then it has, at any point, it has a left-hand limit and a right-hand limit. Now, Something else is that if a function is piecewise continuous on the whole of R, we can take any interval and then find the function there, and in this interval, it should still be piecewise continuous. Or maybe this interval, or any other interval that we can find. Now, what does it mean to be piecewise continuous? Well, it means is you can think of it as the fact that if we take a function, we can split it up into a finite amount of continuous pieces. So, if we look at an example might be like this, where it's going to be defined here, but maybe not here, defined here, not here, and defined at these points. So maybe this is our B and this is our A. So this is an example of a piecewise continuous function. We see that at any point, it has a left-hand limit and a right-hand limit. Even at the discontinuous points, it has a right-hand limit and left-hand limit. But also it has a finite amount of discontinuities. So it has 3 is finite. And so this is a piecewise continuous function. And what it means is that I see a finite amount of disjoint things. So we have this part right here. We also have this part right here. And this part, and then this part. So what it's saying is, if you can look at we can essentially have this function be broken down into different pieces, and we can have each piece by itself. So if you, for example, only look at this individual piece right here, then it's going to be continuous. And if we have a finite amount of pieces, so we have one piece right here, if you look at this piece by itself, it's continuous. We have a piece right here. If you look at it by itself, it's also continuous. This piece is also continuous, and this piece is continuous. We have 4 continuous pieces. That's a finite amount, and so that's what it means to be piecewise continuous. Although you don't need to know too much about it, because the reason we look at piecewise continuity is because if it's piecewise continuous, it means that we can actually integrate it. So what are functions that we can't integrate? Well, generally, what we're looking for is functions that aren't maybe infinitely discontinuous. So maybe some function that goes like this towards 0, which can be seen in something like x, sine 1 on x. So this is not integrable, just because it has an infinite amount of jumps. And something else is maybe like 1 on x, because it goes to infinity. So you can't have an integral from 0 to infinity of 1 on x, right? Because it goes to infinity right here. So since it goes to infinity, we say that the right-hand limit doesn't exist. So as long as we avoid these kinds of topics, then we should be able to say that the integral from a to b exists, which is what we're looking for. So why do we want to know if it's possible to integrate from a to b? Well, if f is continuous, then we know that since cos and sine are continuous, these right here are continuous, right? And so if those are continuous, well, piecewise continuous, we can integrate them. And you might notice that these integrals are how we find the coefficients. So this means that we can find the corresponding coefficients for Fourier series, but just having it be piecewise continuous doesn't mean that it will converge at every single point. So we need a stronger condition to make sure that it will converge, and this is called piecewise differentiability. It's very similar to piecewise continuity, except it's just a left-hand derivative exists and a right-hand derivative exists, and it's not derivative on at most a finite amount of points. So we have a similar theorem. If a function is piecewise differentiable on all of R, we can take any subset of R, and in that range, it will be piecewise differentiable as well. And something to note is that the limit of our derivative at x is not equal to, so I think this should be d plus f of c is not equal to the limit of our derivative function. So that's something important to note. So let's look at C. Let's look at pointwise convergence. And it's essentially saying, how would a Fourier series converge? Well, we have a couple conditions. If it's 2L periodic, if f is piecewise continuous within the range minus L to L, and if it's piecewise differentiable, then we can say that the Fourier series, so generally the Fourier series is represented as an S, and then we have a subscript f, which is the function that we're finding the Fourier series of. And what this says is, if we have a function, maybe like this, the Fourier series at point C is going to be this point right here. So that's if it's continuous. And if it's not continuous, it's going to be the average of the left-hand limit and the right-hand limit. So what this means is, maybe we have something like this, right? So maybe this is our original function, f of x. In our f of x, in our Fourier series, what we find is that we have these two branches as well, but what it does is at a discontinuous point, so right here, it takes the average of the left-hand limit and the right-hand limit, so it just takes the average between the 2 points right here. So this would be what the graph of our Fourier series is. Now we can look at uniform convergence. So honestly, we don't really need to know what uniform convergence is defined to be. What's more important is, how do we know if something is uniformly convergent or not? Well, we know that something uniform convergence will preserve continuity. So what this means is, if f of k is continuous, but let's say f is not continuous, so if the Fourier series is continuous, but f is the function that we're trying to approximate is not continuous, then it cannot converge uniformly. So this is important for questions like these. So generally in your Fourier series questions, there's going to be like a part C. It's just going to say, hey, does this Fourier series converge uniformly? And you have to give reasons to whether it does or it doesn't. In this case, we have the same question that we just did. And what we might see is that, no, it does not converge uniformly. And the reason is because from A, we see that f is discontinuous at pi because it was something like this, right? So obviously, since it's a discontinuity, it's not going to be able to converge uniformly. And of course, our Fourier series is a sum of sines and causes, so it's continuous. And of course, right here, this is generally what you would write in your exam. Just one is discontinuous, the other is continuous, so it cannot converge uniformly. Now, there's also a Weierstrass test, which is a way we can see if a given function, if a given Fourier series actually uniformly converges. So what it means is we essentially just find a bigger series that also converges, and this series has to be bigger than our Fourier series. So that just shows us if this larger term is convergent, then this smaller series must also be convergent. So we have a question right here from 2018. It gives us a Fourier series, and we just have to see, does it uniformly converge? Well, we can take the Fourier series right here, and we just need to see if this sum right here uniformly converges. And the way we do that is we take this term right here and see if it's bounded by some term ck, where the infinite series of k equals 1 to infinity of ck is convergent. Well, what we can do is we see that cos is between -1 and 1 always, so we can get rid of it in the absolute sign, and then we can see that dividing by pi makes it smaller. So we know that 4 on k squared is always greater than or equal to our term right here. And we know that 4 on k squared converges by the p series. So since this converges, we can say by the Weierstrass test, SF uniformly converges to F. Now we also have mean square convergence, which just means if we have two functions and their difference squared integral from a to b is equal to 0 as the limit k goes to infinity, then this is going to be convergent in the mean square sense. Now, we also have Parseval's theorem, and what it says is if it's a function is 2L periodic, it's bounded, and the inner product with itself converges. So if f times f integral from -L to L is convergent, then we say that the Fourier series converges in mean square sense or L squared sense. Now we can use it in Parseval's theorem. So essentially, if the Fourier series converges in mean square sense, we can use this formula, which is just the integral of f squared from -L to L is equal to a0 squared times L on 2 plus L times the infinite series of an squared plus bn squared. So let's just quickly use it. We have this Fourier series right here, where it's going to be equal to 1 from 0 to d, but let's note that this is the absolute value, and it's equal to 0 from d to pi in its absolute value. So what it might look like is something like this. So we know that between maybe here and here, which is d and minus d inclusive, so it's closed circle because of this, it's going to be equal to 1, and then the rest of the time it's going to be pi and up to minus pi minus d. It's going to be equal to 0 because of this range, because this just says from minus pi, this should just be minus pi to d minus d, and then d to minus 2 pi, it's going to be equal to 0. So if we just repeat this, we should get that it's going to be 0 until our pi plus d, and then it's going to be 1 onwards until 2 pi. In the same way, it's going to be 0 until minus pi minus d, and then it's going to be 1 until minus 2 pi. Now let's start determining the Fourier series. So our Fourier series, we can just use our formula, which is ak is equal to 1 on L. In this case, since it's 2 pi periodic, we say that L is equal to pi. So we already know this. Of course, we also know that f is even, right? So f is even right here. And so what we can say is that since these two functions are even, even times even gets an even. So we know that the integral from minus pi to pi is equal to 0 to pi. And then we, of course, multiply the integral by 2. Now what we can do is we can separate it from 0 to d and d to pi. And the reason we do that is because f is defined differently in these branches. So we know that when it's between 0 and d, f is equal to 1, and when it's between d and pi, f is equal to 0. So we can just get rid of this term. So we're left with 2 on pi times this cos. We evaluate the cos, and we get this term. Now, we also know that f is even, right? So when f is even, that means all of these sine terms have a 0 coefficient, which is why bk is equal to 0 for all k. Now, we can find out what a0 is in the same way, which is just the integral from minus pi to pi of f times 1 on pi. We know that in these ranges from minus pi to minus d and d to pi, it's going to be equal to 0. So we can just get rid of these integrals. And then we have an integral of minus d to d with 1. So of course that's 2d. 2d divided by pi is 2d on pi. And that's how we get a0. Now we have our Fourier series, where we see the a0 on 2 term, so the 2's cancel out. And then we have our ak times cos. So how do we use Parseval's theorem? Well, first we can see that the conditions for Parseval's theorems hold. So we know that the integral of f squared from minus pi to pi is going to be equal to L on 2, which is pi on 2, times a0 squared times pi plus ak squared plus bk squared. Since bk is equal to 0, we only square the coefficient of the cos. So we can first evaluate the integral. Since it's only defined from minus d to d, that's what we do, and 1 squared is equal to 1. So we can find this integral really easily. We've squared these, so we've worked out what these are. And then what we've done is we've seen that this becomes a 4 on pi squared. So if we take it out, we actually get our term that we're looking for here, right? So now that we've simplified, what we can do is we can just rearrange for this series, and then we should be able to get the answer to this question. So we've used Parseval's identity to find the series, which is going to be equal to pi times d on 2 minus d squared on 2. So now we can graph our thing. So generally, like a huge tip is that it's going to be almost the exact same as your original graph, right? So, except instead at all of the discontinuities, you would draw an open circle, except maybe the endpoints. 2 pi, we have 2 pi here, and then we have minus pi minus d, then we have our d minus d here, we have our d here, we have our pi plus d here. So at every discontinuity, the Fourier series, so please note that we're graphing capital F and not lowercase f, the discontinuities is the average between the two values. So these would be our Fourier series values, which we look for. And that's how you graph it. So you just graph what we did in part A, and then we find the average between the two values to find the Fourier series value. Now, I think we can move on to vector fields. And vector fields is actually a pretty simple topic, I think. A vector field is just a function which has a vector input and vector output, and both have the same dimensions. So you can think of it as every single point in maybe, for example, 3D space has a vector associated with it, which is also 3D. And that's essentially what a vector field is. So, an example of a vector field in 3D space can be capital F right here. It takes in a vector x, y, z, and then it has three scalar functions, f1, f2, and f3, which are the functions for each individual component. So what we see is that it takes in a 3D vector, but then also produces a 3D vector. So how exactly do we draw a vector field? So generally you'll be asked to draw 2D vector fields, and a vector field is essentially just you regularly find points on a grid. Usually I would do maybe the integers, so maybe every integer in a square grid, because usually you'll be asked to draw out for a 2D vector field. And what you do is, for each point, you put it into the vector field, and then it'll output a vector, right? And then you just draw a vector to represent this. You draw an arrow to represent this vector. So maybe it's right here. So generally you draw it in the same direction as the vector. And then we also have a magnitude, which is represented by length. So maybe a shorter arrow means that it has a shorter magnitude, or a longer arrow means it has a much larger magnitude. So how are vector fields used in the real world? Generally, so this is an example of how it's used to measure the wind speeds over an ocean. So you'll see that these arrows right here, they have a bit of a direction. So each one has a small arrowhead to it. And so each of them show their direction. But you might see that these ones right here are much smaller in length. They're almost dots, right? Compared to these much longer vectors. And so we see that length is also used to denote the strength of the wind, so how much faster the wind is compared to other places, as well as direction. Now, we have something called a flow line, and it's defined as a path CT, where the diff of C is equal to F, and the input is C. And what this means is the velocity is determined by the vector field. And how you can think of it as is, if you plop down a point right here, so if you put a point down here, how would it travel through the vector field? So maybe if we put a point here, it would follow the arrows to maybe do a path like that. Since this path follows the vector field, it's called a flow line. And what you might notice is that the actual tangent at each individual point is going to be equal to the vector at that specific point in the vector field. So we also have gradients right here. So grad f is also seen as nabla, which is this upside down triangle times f. And what this means is produce a vector where we diff f with each of its individual components. So if we diff f with respect to x1, that's our first component. Diffing f with respect to x2 is our second component, and so on. And what we might be able to think of nabla as is this vector, which is just partial diffs. So multiplying by f is essentially like we're multiplying the whole vector by f. So each individual component gets an f. And that's how we can kind of think of it as. So now we can go on to divergence. And divergence is denoted as a div and then a vector field f. And it's going to be the dot product between our nabla and then our f. So what we might see is that it's kind of like a dot product, right? It's taking the first components, multiplying them together, taking the second components, multiplying them together, taking the third components, multiplying them together, and then doing the addition, which is why we denote it as a nabla dot f. Well, divergence describes the spread from a point of a vector field, and a positive divergence means that there's a net outflow, and a negative divergence means there's a net inflow. So, also, if this whole thing is equal to 0 everywhere, at every single point it's equal to 0, then we call f incompressible. So this is just one of these definition words that you should know. It's like an exam might ask you, what does it mean to be incompressible? And you should just be able to say, hey, the divergence of f is equal to 0 everywhere. Right? Simple. Now, what we can do is we can see maybe a way you can think about divergence, which is we have a point that we want to find the divergence of. What we're doing is we're kind of drawing a bubble around it, and we're seeing the pressure that it feels. If it feels as if the bubble is trying to expand, right, it's trying to move out, there's a pressure outwards on this bubble, then we would say the divergence is positive. And if we have a bubble, but it feels like it's pressing in on itself, it's trying to collapse or compress, then we say that the divergence is negative. Well, how do we find divergence? Well, they'll give us a vector field. We just find the diff with respect to x of the first function, diff with respect to y of the second function, diff with respect to z of the third function, and that's pretty much it. I mean, I don't think there's too much to be said. It's pretty formulaic. Just remember what nabla is, and that it's the dot product if it's diving, or you can just remember the formula. So, how do we find curl? Well, curl is denoted as the word curl and then an f. So it's also the nabla dot cross product and then f. And of course we see nabla right here with its partial diffs, and then our vector field right here in its cross product. And if we evaluate this cross product, we should be able to get the curl right here. So kind of similar to the divergence, if the curl of f is the zero vector everywhere, then we call it irrotational. And if f is a 2D vector field, generally we let the third component equal to 0 and still calculate the curl. So, how can we think of curl? Well, the way we can think of curl is if we put a paddle wheel onto a specific point and fixed it, in what direction and how fast would it spin? So, for example, if we put a paddle wheel on this specific point and it rotates anti-clockwise, then a positive curl in the direction dotted in the vertical direction is going to be positive. And if it's a counterclockwise movement, then we can say that this curl dotted with the vertical direction is negative. So, there's also a scalar curl, and it's generally denoted by curl, and then we have a z subscript, and then an f, and it's just the third component of our curl. So, essentially what it means is it describes the rotation around a point while looking down on the xy plane. So if you're looking at an xy plane and you put a pinwheel, in what direction would it rotate? That's pretty much it. And so a positive scalar curl indicates anti-clockwise rotation, and a negative scalar curl indicates a clockwise rotation. Well, let's look at an exam question now. So, if we want to find the curl of a vector field, generally we can just write out what curl is. We know that curl is the cross product between nabla and f, and we can write out the cross product determinant box thing and just work out what the cross product is. Then we can just find what the partial diffs are, sum them in. Simple as that. Well, Now, a good fact to note is that if f is twice continuously differentiable, then the curl of grad f is going to be equal to the zero vector. And why is that important? Because sometimes they ask this question, which is essentially, if we let f be equal to nabla f, so capital F, which is the vector field, be equal to the grad of some function f, is it any way that f is twice continuously differentiable? Well, the way we find that is we look at the curl and we see that curl f is actually equal to curl grad of f, because these two should be the same, right? But since this is not equal to 0, we can say that there's no function such that f is twice continuously differentiable because the curl of grad f is not equal to 0. And that's pretty much the end of my part. I'll be handing it off to Tim, who's going to be taking our next.
Alrighty-o, I think that is me done. Get keen for that then. Look, I hope you're all excited to jump into some line integrals, baby. It's line integrals time. Um, Sorry, I just sort of switched brains very suddenly. So, welcome everyone to the second half of Math2011, the second half of the seminar as well. I'm Tim. Big thank you to the absolute unit Ronald himself for taking us through those first couple of sections. I just wanted to check that the sound was working. And I'm going to be taking you through the next two sections, which are line integrals and surface integrals. We're going to have a lot of fun. Vector calculus, very cool, very epic. We'll be rounding it out. So first of all, we're going to be taking a look at path integrals. So a little bit of quick recap. A path is just any sort of description of a curve. It's sort of like a formalization of beforehand. You might have had like big wiggles that go around in circles. Wow, a path is just a way of mathematically describing those. Now, I'm not going to lie, almost all of the questions you're ever going to like encounter in this course are either going to have paths which are just a straight line or paths which are just a circle, because they are really easy to describe, and like we want you to focus your time, like it's more valuable that you spend your time doing fancy vector calculus stuff than figuring out, oh my god, how do I figure out the parametrization for this particular line? Like, you don't have to stress too much over how to parametrize a line. Basically, a curve is just a way of describing a particular little squiggle they have to do math with. Now, a path integral is just a normal integral, but instead of taking your integral with respect to like the x, y, or z plane, you're taking it with respect to your funky wonky path. This is really cool. This is really useful because in real life, a lot of okay, on the one hand, in real life, there are a lot of situations where you do have like a natural x, y, or z plane. There are also a lot of situations where you don't, and so that's essentially, I guess, that's kind of the TLDR for most of what I'm going to be talking about today. It's just like we're dealing with situations where we don't have nice, neat, flat baselines, and so we have to do integrals over funky shapes, is essentially what I'm going to be talking about. Now, a path integral is given by this formula, where essentially you have your function in terms of f, uh, like f in terms of x, y, and z. You take your curve C. Let's say your C looks kind of like this, has some kind of start point A, some kind of end point B. You parameterize it over whatever your curve is going to be. Like I said before, most of the time it's going to be like straight line from A to B, and then you, like, let's call that path C of t. You then take the derivative of it, find the absolute magnitude of it, and then substitute your expression in to the piecewise components of your function. That then gives you something that you can substitute in and integrate that now like normal looking integral, and you can integrate it from your start point over to your end point, which is very, very cool. Just to sort of be very specific though, when I have a and b in this integral here, that's sort of like the start and end point of my t rather than the start and end point of my like values. It's essentially the values that I parameterized my curve for. Once again, just like how normally our parameterization is going to be a straight line going from a to b, our t is normally going from 0 to 1. The reason for that is a really, really easy approximation for a parametrization going from a to b is just a 1 minus t plus t times b, because you can see when t is equal to 0, then b disappears and we're just left with exactly a. Then as t goes from 0 to 1, we sort of smoothly move down this line, and then when t is equal to 1, all we're left with is b, and we don't have any more a, which is very cool. Okay, path integrals. So note that the value of the path integral is not affected by how we parameterize the path. In fact, as we'll see, sometimes it doesn't even matter what the path is itself. So for example, if like fy and z is equal to 1, then we can get the length of c. Essentially, one really nice integral that you get is like you can get that formula that you may remember from 1b. And then you can also split out constant factors and do additions and do funky stuff like that. To be honest, most of the questions that you'll encounter in this course probably won't need you to do a lot of that sort of stuff, but this is just maths, like tips and tricks. Essentially, sort of like how, I guess how like you could integrate, like let's say you've got an integral that goes from like 3 to 7, like a normal integral. You can split that up into like the integral from 3 to 5 plus the integral from 5 to 7. In the same way, if you've got an integral that's made up of two different curves that sort of join nicely together, you can integrate over one of the curves and then integrate over the second curve, which is very, very cool. Now, a line integral is similar to a path integral, but instead you integrate over a curve in a vector field. So essentially, this function here, I don't know if I explicitly said it, but this is a normal scalar function. A path integral is the exact same thing. It's just that, sorry, a line integral is the exact same thing. It's just that instead of having a normal scalar function, we have a vector function instead. And this is where I guess most of your situations are more likely to come into. The only real difference between we take our curve that we're integrating over, we parameterize it, and then we like figure out what its derivative is instead of multiplying it by the absolute magnitude of the derivative, what we do instead is we dot product it with our derivative, which is very, very cool. Now, C of t does, in this case, need to be continuously differentiable. It just needs to be we need to be able to differentiate it because our formula calls for us to differentiate it. Like, if we can't differentiate it, it's going to be slightly annoying to actually be able to find the derivative of it in the first place. And our parameterization needs to go in the same direction as the original curve. So one of the fun things with curves and also with normals in this section of the course is that they do have a direction that we do care about. I don't want to say don't worry about it, because sometimes in like exams and stuff, they might try and catch you out by giving you the wrong direction or like the oppositely oriented curve. But a lot of the time you can just sort of look at the orientation just to sort of check off in your mind, oh yeah, we've got the normal orientation. But most of the time you don't have to stress too much about actually like doing things with it. You can just sort of look at it and be like, oh, it's cool that that's there. Don't care about it anymore. If it says that it's the opposite direction, you can just like chuck negatives and stuff. It's not the end of the world. And finally, the line integral can sort of be thought of as the integral of the tangential component of f. This is something that's really only going to become important when we're integrating, like, I guess if there's a question that gives you some kind of physical thing, we'll do an example in a second. But essentially what that's saying is we're integrating over whatever component of the force is tangential to our Essentially, if we've got a force field that looks like this and our path is going across like there, then here we're integrating across the entire force field. Here we're only going to be integrating over like the little component that sticks in this direction. Here we're only integrating over the little component in this direction. Here we're only integrating over the little component there, and there, and there, and so on and so forth. One thing you might notice is here, of course, there is no tangential component, like especially here, there's no tangential component of the force field to our line, so therefore like the integral at that particular point is going to be 0, which is very, very fun. Now, one quick thing on line integrals. Line integrals, you often write them in this particular form here, the integral of m dx plus n dy plus p dz. The reason for that, and then there's also a parametrized version of that. The reason for that is just because of the form of our integral in the first place. Because usually if you've got like some function in terms of like some function of x, some function of y, some function of z, and then you have it with derivative of like x, derivative of y, derivative of z. When you split it up, you're going to end up with like some function. Actually, it's not even that function x, y, and z. Like these functions don't necessarily have to be functions of x, y, and z. Like just some component m, some component y, sorry, some component p. When you dot product these two together, you just end up with m dx plus m dy plus p dz. Now, that's not super nice to integrate, so that's why we use the parameterized version instead. So if we parameterize the equation to give us some function x of t, y of t, and z of t, then all we're doing is dot producting what we get when we substitute that expression in, multiplied by the derivative of x of t, y of t, and z of t, which is now an integral that is entirely in terms of t, which means it's something that we can integrate, which is very, very cool. One last note in terms of like what does this physically mean? Like I know that most of you are probably math students and you don't care too much about this. But the work done by a vector field f along the curve is given by the line integral f over c. It's sort of like that's one of the main physical interpretations that we use this for. Which is very coolios. It's for allowing us to calculate the work. It's sort of like, as we'll see later on, you can also do stuff to calculate fluxes and cool things like that, which is very cool. Now, I have talked to you a whole lot. I've spat a whole bunch of definitions, but we haven't actually done anything. So let's dig our teeth into a hot, spicy, juicy question. So let C be the oriented curve in R2, which is formed by tracing a quarter of the unit circle centered at the origin anticlockwise from 0, 1 to 0. Sorry, it's from 1, 0 to 0, 1. Let f be a vector field defined as f of xy equals 2x, 3y, and we want to evaluate that curve there, which is very, very cool. So the first thing we need to do is actually parameterize the curve. Now, like I said beforehand, most of the time we're either going to be dealing with a straight line or a circle. Wow, here we're dealing with a circle, so the parameterization that we can use, note that it's in 2 dimensions rather than in 3, so all we have to do is our normal circular coordinates. We can express this as c of t is equal to cos of t sine of t, which is really lovely because as t increases, as t goes from 0 to 1, as t goes from 0 to pi on 2, we can see that our cos is going to drop from 0 to 1 and our sine is going to grow from 1 to 0, i.e. we're going to go from our original point 1, 0 up to our point 0, 1, which is in the right direction of our curve. So we don't have to worry. Our parameterization ticks all around is actually going to correctly describe our orientation. And the way you can do that, like, I know we kind of whipped it out of nowhere here, but the way you sort of come up with these parameterizations is usually, wow, it's a circle, let's use some cos sine. If the circle doesn't have a radius of 1, then you chuck the radius out the front as well. If it's a straight line, you go like t, you use the parameterization I gave you beforehand, using like t equals 0 for your start point and t equals 1 for your end point. And of course here we chose t going from 0 to pi on 2 because that means that our curve goes from 0, essentially goes from like cos being 0 up to cos being 1. Cos being 1 up to cos being 0 and sine being 0 up to sine being 1. So now that we've done that, all we have to do is basically chug and plug it into our formula, right? So remember, we can express this as being the integral from a to b of f of c of t dotted with c dat of t dt. So one thing that we have to do then is we just need to evaluate what is f of c of t substituted in and what is c dot of t. So if f is equal to 2x 3y, well then if x of t is equal to cos t, y of t is equal to sine t, we can sub those in as 2 cos t and down here as 3 sine t. One thing you'll notice about this question, and honestly, look, I don't want to give vector calculus a bad name, but most of vector calculus is very, very formulaic. Like, you're not going to have to do a ton of thinking when you're doing this sort of stuff. But yeah, it's mostly just you get your parametrization. That's the thinking done. Now it's just chug and plug into the formula. So now we've done that, let's differentiate t. So that gives us minus sine of t, cos of t. Then we dot product these two together, so that's like 2 cos of t, 3 sine of t, dotted with minus sine of t cos of t, which is going to give you minus 2 cos of t sine of t plus 3 sine of t cos of t, which is equal to, I've been saying t a lot, which is equal to sine of t cos of t. Now that's our stuff inside the integral sign, which means what we're going to have to do is integrate that bad boy from 0 to pi on 2, which is very, very fun with respect to t. So chuck that integral bounds on. We're going from 0 to pi on 2 of sine t cos t dt. Now, this is kind of at face value a fairly gross integral. The way I'm going to integrate it is using the fun fact that sine of 2t is equal to 2 sine t cos t. I've been saying sine t cos t so much, but we can substitute that in to say that this integral is going to be half the integral from 0 to pi on 2 of sine of 2t dt, which, just quickly evaluating that, is going to be negative 1 on 4 cos 2t from pi on 2 to 0. Chucking them bounds in, that then gives us, oh man, that then gives us minus 1 on 4 cos of pi minus cos of 0, which is minus 1 on 4 of minus 1 minus 1, which is 1 on 2. Which is very hot, I reckon. That's very nice, assuming, of course, that I've done my maths right, which I have, which is very, very cool. So yes, we solve it, which is very poggers. Now, just like we quickly went over those properties for line integrals, sorry, for path integrals, line integrals also have some of the same properties, right? You can have the same, sorry, you can have linearity. You also have the reversing of the orientation, which reverses the sign. That's what I was saying about talking about beforehand, which is like you can just look at the orientation, do a bit of a mental check, like, am I going in the right direction? If you're not going in the right direction, just chuck a negative sign out the front, which is very, very fun. And also in the same way, if you have a whole bunch of curves that add together, you can chippity chop it into as many pieces as you like, and that will make it very fun. Okay, quick thinking question. So consider the vector field g of xy equals 1, 1, and the curve C shown in red below. It's a rectangle without one side. Is the line integral over this particular curve positive, negative, or 0, and why? Now, if you're watching this in the future, I want you to pause and have a bit of a think about this one, right? Because, like, I'm about to go through it with you, but I want you to, like, think about this because I think it will reveal to you, do you actually sort of understand what these line integrals really represent. If you want to, like, mentally write down, is it going to be positive, is it going to be negative, is it going to be 0, and why? Now let's go through it. So one big thing that you can see is that our vector field is this like nice uniform thing going along the positive x equals y plane. And our integral consists of three little parts, one going in this direction, one going in that direction. Both of those are tangential to the curve, and then one thing that is going kind of normally to the curve, i.e. at a perpendicular angle. Now, because this thing is entirely tangential to the vector field, if you integrate along it, you're just going to get like essentially you're integrating along that vector field along the particular line. So you'll get whatever that's equal to. Let's say it's equal to like 3. Because this like other side is going in the exact opposite direction, you're also going to get the same magnitude, but you're going in the opposite direction. Now remember, we set up here, if you're going in the opposite direction along the same thing, it's going to be negative, which means this little section here would be like a negative of whatever the first one is. In this case, it's like a -3. Um, and then finally, because we said earlier, right, what we're effectively doing is we're integrating over the tangential component of our curve, which is this little thing, where when we integrate along this little like bottom line here, we're integrating over a thing that is normal to the curve, which means we're not actually going to get any of the tangential component, right? Like where the tangential component, if we're looking for the tangential component in this direction and our original vector is pointing like that, well, the tangential component is 0, so it's like we're integrating over 0 over however long that line is. So this section is just going to be 0. So when we do our line integral and add them all up, remember you can sort of think of the full integral as just being the sum of all of these three, right? Because we can split it up into our different curves. We can say it's this one plus this one plus this one. We're going to get 0 minus 3 plus 3, which is 0. And so voila, we can say, wowzers crazy, the line integral is going to be 0. Because of those reasons as given there, which is very, very fun. Now, one thing that you may notice about line integrals and path integrals, well, specifically, I guess line integrals in this case, is that like they don't take a lot of like deep thinking, but they do take like a reasonable amount of time. Like obviously I wasn't going at the speed of light when I was answering this question up here, but like what you saw was like, wow, that's like a fairly fat amount of like that's a beefy quantity of fairly beefy quantity of working out just for one question, right? So one thing that we have to sort of simplify our working out here is the fundamental theorem of calculus for line integrals. Now, basically, if you remember, your fundamental theorem of calculus was like, if you have some kind of like, sorry, basically was that idea that like if you're integrating from like a to b over f of x dx, where like f of x is equal to the integral of f of x, then you can substitute like big X is going to be big B minus big A. In the same way, we have a very similar rule for our line integrals, which basically says if you have some sort of function, f, which is the gradient of another function, then when you integrate over that function, you end up with the little phi substituted in for your endpoints of your curve. So sort of like your curve here goes from some point P up to some point Q. Well, if you integrate over it, you get like the point P substituted in and evaluated at that particular expression, and the point Q evaluated at that particular expression as well. Now that brings up a quick little thing, which is that like being able to quickly recognize whether or not a function is the gradient of another function is actually a fairly nice skill to have in this course, because it will allow you to really, really rapidly answer questions like this. Now, not gonna lie, sometimes in an exam they may set you up for this where they'll be like, wow, find the function that it's equal to and then evaluate the path integral. But sometimes they'll just like drop you in cold and be like, evaluate the path integral. And so you may have to go through and do some gross evaluation. Or you may just be able to look at a function and say, hey, it's the gradient of this other thing, therefore I can sub in my two different points. Another really quick thing that I didn't explicitly say is that one of the really cool things we notice here is that it doesn't actually matter, like this integral here doesn't actually matter on the about like what the curve is that we're taking. Like it doesn't really care about what C is. All it really cares about is what our endpoints are. Now that's a property of what's called a conservative field. That if you've done physics before, it's essentially sort of similar to the idea that it doesn't matter if you're in like a conservative force field, it doesn't matter where you move. Like the net force or the net work done on a system the net work done on a system only cares about our start points or end points. That actually comes from this idea here, which is that if our vector field is conservative and we integrate over it, we don't care about what the actual curve is. All we care about is the start point and the end point, which is very, very fun. TLDR from that is essentially if your function is the gradient of another function, you can just substitute in your like endpoints of your function. I guess one thing to sort of see why this helps is you can say, now this is very illegal in vector calculus terms, so like please, dear God, do not copy any of this down in your exam. But if you sort of think of your gradient as being your derivative, you can think that like the integral of that is like the integral of your derivative thing. And if you remember back from like single variable calculus, if you integrate over dy, that's equal to just like y. In the same sense, these two things disappear, so your integral of f is just equal to your little phi. That's sort of why that helps here, which is very, very cool. Now doing that, let's have a go at this question. So let f of x equal x, y, and z. Oh, sorry, one quick thing that I didn't mention, and I'm not sure if Ronald may have mentioned this beforehand. Sorry, love you, Ronald, but as you saw from the start of the stream, I was deep in some other maths work, right towards the end there. But essentially, one of the really quick ways that we can show that a function is equal to if you ever want to rigorously prove that the function is equal to some other gradient function, you can take the curl of the big F, because there's this really cool theorem which says that the gradient functions are irrotational. So essentially curl times nabla of phi is equal to 0. That was the weirdest phi I've ever written. So in the same way, if you want to check whether or not f is a gradient function, you can just take its curl, and if you show that the curl is equal to 0, then you have proven that it is in fact a gradient function. Coolios. Then, now let's actually have a go at evaluating this line integral along the straight line segment connecting the point A equals 0, 0, 0, and the point B equals 1, 2, 3. Now, in my slides here, I've chucked out some sort of full length working out for this. So if you want to have a go and look through that, feel free. What I'm going to try instead is I'm going to have a go at solving it in a slightly different method, and a method that maybe I would argue is slightly nicer. Now, I guess the standard way of solving the question is you would just go, you would parameterize your curve, and you would substitute in your like expressions, basically solve it like I did the last question. What we're going to try and do instead is we're going to try and find what the function is that like this function is the gradient of, and then we can substitute in the points 0, 0, 0 and 1, 2, 3. Now, in order to do that, you basically have to take each of your points, and you're going to integrate them with respect to like their respective components. So you can sort of imagine if we have like, I'll just start off with the x component. I don't know why my thing isn't rubbing out. Oh well, it doesn't want to disappear. Okay, so let's say we are like assuming hypothetically that f is equal to some function phi. Dude, my rubber is okay. My rubber has just decided to not work. So we're gonna have to bear with that. We're gonna have to cope. Okay, so let's say we're gonna have to accept the disgusting looking phi's that are really looking like epsilons at this point. Like, what is that? If this is true, like hypothetically, if that thing there is true, then we know that like the partial derivative of x, sorry, the partial derivative of this like first function f with respect to x is equal to y. And therefore, because of that, we can say that the partial derivative with respect to x, we can sort of just do some quick back mental arithmetic. We can say that the original function was probably equal to some y of y times x plus then some function f plus z. Now, I didn't actually try this before the lecture. I was just like, in the moment just then, I was like, hey, that might be a cool way of doing this. Now I'm realizing it may not be as simple as I had originally hoped. So we may be going to do this back in the good old classic way of just doing the line integral the main way. Essentially, there are going to be some questions where it is easier to just straight up find our sigma, and it turns out that this is not one of those cases. So, or at least I can't see if it's one of these, what nice one of these cases or not. Okay, so let's have a go at solving this question, I guess the normal way. So, if our parameterization is the function c of t, where c of t is going to be equal to a times 1 minus t plus t times b. We can substitute in that a is equal to 0, 0, 0, so this whole thing is just going to disappear, so then it's just going to be t times 1, 2, 3, which is very fun. Very, very exciting. And then in the same way, we can then differentiate it. So we can say c dot of t is just going to be 1, 2, 3. And we can substitute it into our function. So we can say f of c of t is equal to whatever y of t is. So that's 2t. X of t is 1t, and then 2z is going to be 6t. So now we're just taking the dot product between 2t, t, 6t, and we're dotting 1, 2, 3, which is going to be equal to 2t plus 2t plus 18t, which is going to be 22t, and then we're just integrating that from 0 to 1 dt, which is going to be 11t squared from 1 to 0, which is 11, which, you know what, I think doing it that way made it probably a little bit nicer. So that's how we can integrate the line integral. And now we have to show that the value of this integral is the same regardless of the path taken between a and b. Now thinking about how we might, what this question is essentially asking us, right? Because like you may look at that question and be like, what the hell? How am I supposed to do that? How do I like prove that it's the same for every single path? Like I don't want to have to evaluate it for every single path possible. Well, remember, all we essentially are trying to do is show that it's the same for every path, i.e. show that it's a conservative function. And the way that we do that is by just showing that there is some like function phi such that f is the gradient of it. Now, there are two different ways you can do this once again. You can either actually obtain that function phi in the first place, or, and this is probably the way that I would prefer to do it, is just show that the curl is 0. Show that the curl of f is equal to 0. That then means it's a conservative function, just because it means that it's equal to some gradient function, which is very, very cool. So to do that, we're going to take the cross product of nabla with f. Evaluate this however you prefer to evaluate your curls. Look, people judge me for the way that I do my cross products, but I do it like good old Wolfgang taught. No, it wasn't Wolfgang. It was Pinchas Grossman. Sorry, my voice just died then. All right. Cool. We're back on track. Taught me back in Math 1A, the absolute mad lad himself. Anyway, we're taking the cross product of x, y, and 2z. I like to do cross products by basically doing crosses across my things. So it's like the derivative of 2z with respect to y is 0, derivative of x with respect to z is 0, then you do these two, it's still all going to be 0, then you do these two, and it's going to be the derivative of x with respect to x is 1, minus the derivative of y with respect to y is also 1, which gives you 0, 0, 0, which is the 0 vector. Therefore, the TLDR from that is that means that this thing has to be some kind of gradient function, which means it's conservative, which means it doesn't matter which path we take, which is very, very fun. Of course, you can go through the normal way and actually figure out what the original function is going to be, but that's long and hard, as you can see from my slides here, and I much prefer just taking out curl, which is very, very exciting. Okay, let's look at one of the best theorems that we get to deal with in this course, which is Green's theorem. Because Green's theorem is another really nice way for finding line integrals on vector fields with complicated components that have much simpler partial derivatives. Basically, it's a thing where you look at the function and you're like, man, if only I could do some partial derivatives on this thing. So there are a whole bunch of conditions. Your conditions are you need a nice bounded simple region where C is like you have some boundary C, you have two functions M and N which are continuously differentiable. Then, and this is what Green's theorem says, Green's theorem says that the integral, the line integral over this looking expression here is equal to the partial derivative of the y thing with respect to x minus the partial derivative of the x thing with respect to y, and then you just take the double integral over its area. So essentially, if you have some surface that looks like that, which is over some gross ass looking vector field, instead of actually evaluating that, you take the double integral over the area of the partial derivatives. And this is like almost cracked difficult because, sorry, this is almost cracked in how like much nicer it can make things, just because you may remember that like if you take the partial derivative of things that like are mostly in terms of y, for example, and you take the partial derivative in terms of x, like all that y stuff just disappears. And so that happens like a fairly substantial amount, which means that you can basically just chug and plug, and almost all the time. I just realized my eraser's back. Woo! Can we get some like hype in the chat for eraser coming back? Big fan of that. Anyway, so we chuck that in, and then we evaluate our integrals, which is we can then just do the double integral, which is very, very fun. Once again, Green's theorem is almost too formulaic in the sense that it's just our like partial derivatives subbed in with respect to each other, which is really, really cool. So let's have a crack at actually using Green's theorem, and here you're gonna get like absolutely mind blown by how lovely this is going to be. So let C be the circle, x squared plus y squared equals 4, oriented in a clockwise direction. Use Green's theorem to evaluate this integral here. Now, I take 2 seconds, I take half a second, half a millisecond to look at this function and go, I don't have to like do like a freaking T sub and then integrate like those suckers. That looks disgusting. That looks absolutely horrific, right? Because yuck, that's just so gross. I don't want to have to deal with that. I don't want to have to do anything with that. Like yuck, 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 yuck. So instead of actually having to do it the normal way, your boy turns to Green's theorem and says, okay, let's split this up into our m and our n, take some partial derivatives, and then chuck them into Green's theorem, and we're gonna have a little bit of fun. So first of all, you look at the thing that's attached to dx. In this case, it's this section here. So we can call m as y plus e to the x squared sine of 3x. Look, I may have gone a little bit overboard writing this question. And then we call n this little component here. So n is equal to 2x plus sine of y squared cos plus cos of y. And just to sort of get a feel as to how good Green's theorem is going to be, like this is a circle oriented in a clockwise direction. So our substitution would be like c of t equals, we're going to use like cos t sine t again, which means once we start subbing things in, like this expression is going to be sine of sine squared plus cos of sine y. Like, I don't want to have to integrate that. Like, no. So instead, what we're going to do is we're going to take some partial derivatives. So first of all, our partial derivative of n with respect to x, well, you see, this is all in terms of y, so our partial derivative is just 2. And similarly, our partial derivative of m with respect to y, this is all in terms of x, so that's just 1. So when we do our del n del x minus del m del y, we end up with 2 minus 1, which is just 1. So all of a sudden, this is equal to the double derivative over d of 2 minus 1 times dx dy, which is literally just the integral of d dx dy, which remember, if you're integrating over like d dx dy, it's just the area of d In this case, the area of D is a circle with a radius of 2, so it's going to be like pi times 2 squared, which is just 4 pi, which is like so much nicer. Yes, Green's theorem. I stand Green, all right? Whoever Green is, I feel like I remember when I did this course, they went through like, hey, like Green had like this mill. Also, I didn't actually check who the lecturers were this term, but like Goyen, absolutely king. Like, holy moly, I love Goyen. I aspire to be like Goyen, all right? Anyway, yeah, Green's theorem, very poggers. You get 4 pi instead of having to do all that fun stuff. All right, back on track. It's time for surface integrals to round out this whole topic, our last topic, which is surface integrals. So similarly, how a path integral is the integral of a scalar or vector field over a curve, the surface integral is the integral over a surface instead. I guess it's sort of like if you think of, I guess this is not a great analogy, but it's sort of like if a line integral is the funky curve equivalent of like a normal integral, surface integral is like the funky curve equivalent of like a double or volumetric integral, which is very cool. Now, you basically can use a very similar process to what you had to do for line integral, where the first step is always to find some parametrization of the function, and then you find a normal to your surface. So what the derivative was essentially in the line integral was finding a tangent to the surface. We want to find some sort of like how in your line integral you had to find your derivative, which was sort of expressing what like a tangent to the like curve was looking like. In the same way, here we want some kind of vector that is going to entirely encapsulate what our curve looks like, or in this case, what our surface looks like. Now, because we can't have a tangent to our surface because like our surface is moving in lots of different directions, what we do instead is we find the normal to the surface. And the way we do that is by finding the tangent in 2 different directions and taking the cross product of those 2. So yeah, we can use this fun, lovely formula, which may look kind of gross, and not gonna lie, it is kind of gross. But like it's not, I guess, disgustingly gross. So essentially, it's the integral of you take your parametrization, and you do the double integral over instead of the single integral. You do the double integral over substituting in your parametrization into your function, and then you multiply it times the magnitude of your normal, which is very, very cool. Just a quick note on notation. One thing that we'll often use is instead of writing out the full u cross uv, we write that as just the normal of u and v as well. Now, in the same way that you can write the length of your line as being the magnitude of the derivative of c of t times dt, you can also calculate the area of the surface using this formula here, which is very, very cool. So, yes, if the surface is smooth, we can parameterize it very nicely, where, yes, D is an elementary region. Basically, your parameterization, sort of in the same way as to like how most of your parameterizations for curves were either circles or straight lines. Like most of your parameterizations for D are either going to be like r theta, like essentially your parameterization for the area of a circle, or like parameterizing. I mean, honestly, I think that that's most of them. I think like now that I'm actually thinking about it, I feel like most of the ones that I use are just parameterizations for a circle, and if it's not a circle, then you're going to use one of the other 2 theorems that we'll talk about in just a second. So let's actually do a bit of practice. Let's calculate a surface integral. So consider the surface given by z equals x squared plus y squared. For x squared plus y squared less than or equal to 1, we want to calculate the area of the surface S. Now, the first thing that we absolutely have to do is we need to find our parametrization. Now, in this case, because it's a circle, a really nice parametrization is probably just going to be r theta, where I guess we can say 5 r and theta is equal to r cos theta, r sine theta. For because we're trying to fill out this entire circle, we can say r is going to go from 0 to 1, and your theta is going to go from 0 to 2 pi. Essentially, it's going to go the full way around, and your r is going to oscillate between 0 and not oscillate. It's going to vary between 0 and 1. Now we've gotten that out of the way, we need to find our two derivatives. So our tangent to the curve along r is going to be the partial derivative of r cos theta with respect to, actually, our two tangents, sorry, two tangents. Our formula was, I'm mental blanking. Oh, we have to differentiate the whole thing, sorry. We differentiate the entire thing with respect to r, so that is going to be cos theta sine theta, and our tangent with respect to theta is going to be r sine theta, no, minus r sine theta and r cos theta. We then take the cross product of these two. Wait, have I done something wrong? Because I am feeling like I have done something wrong. Yes, we need to express it in terms of z as well. That was the big oopsie doopsies that I did. Okay, let me work through the solutions that we've got here instead. So I was feeling like, yes, I have made a mistake, but I couldn't exactly see where it was. Okay, we can parameterize it with x, y, and x squared plus y squared. Then we get those two little substitutions there, where our absolute magnitude is equal to the square root of x squared plus y squared plus 1. I apologize if I'm rushing a little bit. I just do realize that we've gone over 2 hours now, so I do want to wrap it up. So we can take the absolute magnitude of tx cross ty, which gives us that little square root bad boy there. And then our area is going to be equal to our magnitude of that disgusting integral there. Now to actually take that integral, one thing you can notice is because our integral is in terms of the square root of a couple of things squared, we can use our polar coordinates, r cos theta and r sine theta. I think that's where I was getting our idea of using the polar coordinates beforehand, where r is going between 0 and 1, and pi is oscillating between either negative pi and pi or 0 and 2 pi. Now, the determinant of the Jacobian of that transformation matrix is r. You can derive that every single time, but honestly, I would recommend just memorizing it, because like sort of your two transformations you're gonna do a lot is just polar coordinates and like spherical coordinates. So if you just know what their determinants are, then it will save you a lot of strife and a lot of hassle, which is very fun. You substitute all that in, and you end up with your expression there. You end up with your final integral being pi on 6 times 5 root 5 minus 1. Essentially, if you can actually find if you can find your parameterization correctly and not just trust yourself to come up with it there when you're rushing, like I did, then it's pretty straightforward and pretty just plug and chug, which is fairly nice. Now, we can also take surface integrals over vector fields, not just scalar integrals, where essentially it's the dot product of our normal rather than the absolute magnitude. Like essentially in the same way that we've got the relationship between line and path integrals when we're doing a surface integral over a vector field, we dot product with our normal rather than taking the absolute magnitude instead. Now, when we are doing surface integrals over vector fields, we actually have a couple of really, really hot theorems to help us along with. One of which is Stokes' theorem, which is very, very cool, because it allows us to compute line integrals over closed surfaces using surface integrals instead. So if S is a smooth oriented surface, and it has some boundary and it has a nice differentiable vector field, then Stokes' theorem says that this relationship is going to be true. And you can use it in either direction. Essentially, if you have some kind of surface integral that is super, super gross, then that like is also equal to the curve another function, then you can evaluate its line integral around the area. Or, and this is probably the direction that we tend to use it most in, if you're given some gross looking function here, but the curl of that integral is really, really super nice, you can take the surface integral over it instead, and that will simplify your life a whole lot. So, for example, here, let S be the surface x plus y plus z equals 0 for x and y oscillating between 1 and 0. We want to take the normal component, we want to have our normal component to be positive. We have some gross ass looking vector field like that. We want to use Stokes' theorem to determine the line integral there. Now, essentially, we look at this function, we're like, yuck, that's gross. I don't have to do the line integral over that. So instead, what we're going to do is we're going to use Stokes theorem, which is very, very cool, because what it allows us to do is take the surface integral over the divergence of this function rather than actually like having to find some gross looking thing. So quickly doing our divergence of f. So once again, you'll get to bear witness to my gorgeous, gorgeous, gorgeous um, method of calculating cross products. I'm sure some people think that I'm just like, I'm sure like some of my teachers in exams like look at me calculating stuff, cross products and just go, yeah, like he definitely just chucked that into an integral calculator, didn't he? But no, I promise you I didn't. Wait, is that 2? No, that's y, x minus y. Um, minus y. Anyway, just for the interest of time, sorry, I'm now realizing that doing it by hand may be a little bit too long. Anyway, you take your curl, which is very fun. You then need to parametrize your surface. So essentially, right, your surface is oscillating between 0 and 1 across all of your different things, which is very, very fun. You can parametrize it as x, y, and then this is essentially just rearranging for z. This is another common strategy where you essentially just like substitute in x, y, and whatever your z is to get your parametrization fairly nicely. Take your cross product of your two things, then you're going to dot that with your curl that you found beforehand, which gives you a nice, very, very lovely double integral, which is much nicer to solve. Yes, which is very, very cool. Now that you've got your double integral, you can just evaluate it because remember x and y are oscillating between, sorry, I keep saying oscillating. I'm sorry that I do. But it's varying between 0 and 1. You can sub in all of your different components, which is very, very fun and ends up giving you 4 on 3, which is very cool. Okay, finally, because I realize that I do need to wrap up. Our final theorem that we have is the divergence theorem. So, Gauss's divergence theorem allows you to compute surface integrals over closed surfaces. Rather, if you have like some really gross surface integral, you can use a triple integral instead over the 3D outside. It's essentially like if in the previous situation what we were doing was looking at the outside of your line integral and doing a surface of integral over the inside. What the divergence theorem says is it says instead, if you've got some kind of really gross surface, what you can do is you can like integrate over the 3D solid on the outside rather than integrating over the surface, which is very cool. So, and also just quick note, I know that you haven't actually done volume integrals in this course, but like essentially like it's fairly intuitive in that it's the same idea as a triple integral, right? Like you're just integrating over your bounds for your 3 different variables, which is very fun. And also, I guess another side note, once again, not always, but a lot of the time, this ends up just being your like volume, like the triple integral of your volume just ends up being your volume anyway, which is very, very nice. Anyway, the requirements that we need is we need our region to be bounded, we need our surface to be smooth, and we need our function to be differentiable. The reason we need it to be differentiable and the reason that this is called the divergence theorem is because the surface integral is equal to the triple integral over the divergence of f, which is very, very fun. And honestly, this is probably my favorite of the theorems because it just makes life incredibly easy. So I'm actually going to, I'm sorry if there are people waiting for the next stream, but I'm going to do the whole question. So let W be the unit disk in R3, i.e. it's the unit sphere plus its entire interior. Let S be its surface oriented so that the normal vector is pointing outwards. Let F be the vector field determined by that. We want to use Gauss's divergence theorem to calculate this thing here. Well, wow, we're going to use Gauss's divergence theorem by basically saying if you take the triple integral over the surface of the unit sphere, then it's going to be the divergence of f integrated over that volume. And the reason this is so nice is because taking the surface integral over this is going to be really gross, but if we just really quickly calculate the divergence, it's going to be 2 plus 1 plus 1, which is equal to 4. So it's going to be the integral of 4 dv over our area of the unit disk, which is going to be 4 times the area, sorry, 4 times the volume of the unit disk, which is equal to 4 times 4 on 3 pi cubed, where r is equal to 1, which is going to be 16 on 3 pi times units cubed, which is very, very hot. So yeah, I guess what I wanted to show you here was like we had this really gross surface integral with this really gross function, and I smashed that out in like 2 seconds. Because Gauss's divergence theorem, very, very poggers, very, very which is very, very exciting. Now that brings us to the end of all the content for Math2011. And we have a very, very special guest, sorry, a very, very special gift for you all, which is that we just released a very, very hot revision sheet for Math2011 that summarizes all of the most important formulae in this course, because one thing you may have noticed from vector calculus is it's very, very formulaic, and there's a lot of very, very formulaic stuff. So if you want to scan the QR code below to visit our website and download this sheet, you can also go to the website to download all of these slides, which is very, very fun if you want to. But otherwise, that brings us to the end of the revision sheets. I want to give a massive thanks to everyone for watching, whether live or in the future. I also want to give a massive shout out to all of my fellow people who have walked us through the course, and Lockie, Jason, Ronald, and I guess. Thank you all very much for watching. Go smash your exams, and I will see you all in the next one, which should be very, very exciting. See you